Good evening, everyone. I welcome you to the 10th problem solving session of NPTEL course Combinatorics. So today we'll be discussing problems on discharging method and bit of group action. So let's start. Our first problem is that we are given, let G be a triangle free planar graph, and using discharging method we have to show that G has a vertex of degree at most 3. And second part is, using the first result, then we have to show that such a G, that is a triangle free planar graph, is 4 colorable. Okay, so the solution. So yes, we are given G is a triangle free planar graph. So if it is a triangle planar graph, and if LF is length of a face which is number of edges on boundary of a face, we are given, so since G is triangle free, we have that LF is greater than equal to 3. We have LF LF is greater than equal to 4, because it is a triangle free graph. Any face at least should have at least 3 edges, but since this graph is triangle free, any face will have at least 4 edges, and we have to show that degree of some vertex is less than equal to 3, or which is equivalent to saying that degree of vertex minus 4 is less than 0 for some vertex V. So now we have to use discharging method to show this result. So in the discharging method, what do? First we assign a charge to each vertex and face, then we have this discharging phase, and then the second phase is we have this discharging phase. We distribute charges in such a manner that the total charge, we distribute charge among the earlier charges, so that total charge remains same, and then using that we try to get some result. So in this case, since we have that length of each face is at least 4, and degree of, we have to show that we have at least a degree 3 at most degree 3 vertex. We have to show that dv minus 4 is less than 0. So let us assign following charge. Let phi v is equal to dv minus 4, and phi f is equal to LF minus 4. So we know that this term is always greater than equal to 0 for all F. Now what is the total charge? Total charge is, we sum over all the vertices and its charges, and we add the charge of all the faces. Left. And if we open this up, V belongs to G. Now let's open this up. So we'll get that it is sigma dv belongs to G minus 4 times vertices plus length of face minus 4 times faces. Okay, now we know that sum of degree of all vertices is twice the number of edges. This is because if we have a simple graph, each edge contribute 2 degree. Hence we see if we sum all the degrees, we will get that it will be equal to 2 times edges. Moreover, length of faces. So if we sum all the length of faces, and if we look at, so we want to compare sum of length of faces and the total edges. So in this, the difference between these two is that here we are counting all the edges, and these counting all the edges which are lying on the boundary of faces, and this counting could be done. So in this counting we could have repeat some edge. So and we know each face, each edge is incident to at most two faces. So we would have count one edge. So in the worst case scenario, we'll see that this total sum will be less than equal to twice number of edges, because this double counting, in the worst case scenario, we would have count one edge twice while counting all the boundaries. So we see that then from this we get that this is less than equal to 2 times edges minus 4 times vertices plus 2 times edges minus 4 times number of faces. And if we further see, this is nothing but minus 4 times V plus F minus E, which is our Euler identity for planar graph. So we see this is 8. So we see that our total charge sigma, this total charge is coming out to be less than equal to minus 8. So this term is non-negative. And we earlier noted that this term, this term is negative. Since this is less than equal to minus 8, so our LHS is negative. But, this term is negative because this sum has to be less than equal to minus 8, so this sum is negative. But this term we earlier noted, the charge contributed by faces is non-negative. Therefore, this term is non-negative. This further implies that dV minus, but since it is negative, so something negative must be coming out from here. So we see that dV minus 4 should be less than 0 for some vertex V. And hence we see that this was what we needed, that triangle free planar graph has a vertex of degree at most 3. Now using A, which is this, we have to show such a G, that is triangle free planar graph is 3 colorable. So it is very similar, is 4 colorable. 4 colorable. So we'll see in the last tutorial we showed that a planar graph is 5 colorable, and to showing that also we use this result that each planar graph should have a vertex of degree at most 5. And so here also, so the proof will go similarly. So last time also once we got a vertex of degree at most 5, then we use the induction. So here also we'll be doing the same. We have now seen that any such graph will have a vertex of degree at most 3, And using induction now we'll show that G will be 4 colorable. So proof by induction on order of G, that is number of vertices of G. So if order G is equal to 1, we have nothing to prove. We can give any of the 4 colors to that vertices. So now assume G is 4 colorable for order G less than n. Now from A we have vertex V of degree at most 3. So consider subgraph G dash induced by V, induced by set of vertices minus V, small v. So we see that G dash has n minus 1 vertices, and by induction hypothesis is 4 colorable. So now all the vertices of G are colored except V. Consider G. Only V remains to be colored. So since degree of V is less than equal to 3, we can choose, and we have 4 colors. So by pigeonhole principle, or we can choose a color which has not been used for any of the adjacent vertices of V, and hence we are done. So we have shown that using this, we have shown that a triangle free planar graph is 4 colorable. So this is we actually know that any planar graph is 4 colorable, but the proof for that is deep. But we can see, for if we assume we add an additional condition on our planar graph that it is triangle free, then it can be easily shown. So now let's move on to the next question. So next question is, we are given we again have a simple plane graph with no cut vertex, and delta G is greater than equal to 3. So that means that minimum degree of vertex, minimum degree is greater than equal to 3. So each vertex has degree at least 3. Then we have to show that G has a vertex of degree 3 on face of length at most 5, or a vertex of degree at most 5 on a triangle. Okay. So we know. So what are the conditions that we have given? We are given that degree of each vertex is greater than equal to 3, and this we already know that length of a face is because a face at least have 3 edges, so length of face is all greater than equal to 3. And we are also given that G has no cut vertex. So recall, if this happens, recall that if G has no cut vertex, then we have 2 facts. First, A, that every face is incident to length face number of vertices. and B, every vertex is incident to degree V faces. So we have this result if G has no cut vertex. Now we need to show that if we have that each degree of each vertex is greater than equal to 3, we have to show that G has either vertex of degree 3 on 5 minus face. So this notation K minus face is basically face with at most K edges on boundary. So we have to show that G has either vertex of degree 3 on 5 minus face or vertex or 5 minus vertex on a 3 face, which is a triangle. So we see here that this question is very much symmetric in the faces and vertices. We have that degree of vertex is greater than equal to 3 and length of face is also greater than equal to 3. This and similarly the result that we want is also symmetric in face. We either want a degree 3 vertex on a 5 minus face or we want a 5 minus vertex on a 3 face. So we have to do we use discharging method for the same. So how do we show such result using discharging method? First, we generally prove it by contradiction. Assume result is false. If result is false, then what can we say that? Then first thing is all degree 3 vertices will lie on 5 plus face. That is face with 6 plus face, sorry. That is face with greater than equal to 6 edges. And all degree 3 vertex will lie on 6 plus face or triangle or 3 face, which is triangle, have 6 plus vertices. So if we assume our result is false, this is what we get, right? G has either vertex of degree 3. So the negation, either vertex of degree 3 on 5 minus face. So the negation of this will be all degree 3 vertices are lying on 6 plus face. And second is that we want a 5 minus vertex on a 3 face. So on 3 face, all the vertices have degree. So we cannot have a 5 minus vertex on 3 face. So if we have any triangle, it has all 6 plus vertices. Now let's give the charge. So step 1 is assign charges. So let's do the same thing that assign the same charges that we used for the previous question and see if they'll work. So the previous charges were that for each vertex we assigned it to be dv minus 4, and for each face also we assigned it to be this. So the question was symmetric. The question was symmetric in vertices and faces. So it makes sense to assign a same charge. And from the previous question, we know this, that total charge will come out to be total charge was coming out to be -8. Total charge was coming out to be -8. Yes. So now the second, now sorry. Now the second step is we have to, now we see that total charge is negative. Total charge is negative. So the second step is to give a discharging rule. Give a discharging rule such that, okay, so this was not equal to 8, less than equal to -8. Now we have to assign a charge in such a way that we end up getting some contradiction, because we have assumed we need to arrive at a contradiction at some case, then our result will be true. So if we want to arrive at some contradiction, the idea is basically, so we see that this total charge is negative. So first we observe that what all things are contributing negative charges. So observe negative charge. So since total charge is negative, something must be contributing negative charge. So what all things are contributing negative charge? So negative charge is contributed by, this thing will be less than 0 if degree of vertex is less than equal to 3. And we have assumed in our question that the minimum degree is 3. So firstly, negative charge is contributed by degree 3 vertex. And secondly, under this term, this will be negative when LF is less than equal to 3. But LF, we always know length of face is greater than equal to 3. So negative charge will either be contributed by a 3 vertex or a 3 face, which is a triangle. So these two type of things are contributing negative charge. So now we want to discharge. Now we want to distribute charge in such a way that these things become non-negative. These things become non-negative, and other things which are already non-negative remains to be non-negative. And if we are able to do so, then we get that this LHS term is becoming non-negative, but if we are distributing charge in such a manner that RHS is not affected, this LHS is becoming non-negative, RHS is negative. So we see that we have arrived at our contradiction. So what should be our discharging rules? So we see that we have a degree 3 vertex which is contributing a negative charge. And what is the negative charge contributed by what is the charge contributed by a 3 vertex? It is degree of vertex of degree 3 vertex is 3 minus 4. So negative charge contributed by it is -1. So first rule is that we are every three vertex is receiving a +1/3 charge from each of its incident face. Each of its incident face. So now, so every initial charge on degree 3 vertex was -1. After R1, we see that since this graph has no cut vertex, each three vertex is incident to 3 faces. And since it is incident to 3 faces, so it is receiving +1/3 charge from each of its incident face. So after R1, charge on each 3 vertex is 0. So first negative charge we have we have turned our first negative charge into a non-negative charge. Now secondly, triangles are also contributing some negative charges here, and we see that triangles are also contributing. Since triangles have 3 faces, so the negative charge contributed by each triangle is -1. So now we have to make this positive. So now each triangle will be incident to 3 vertices, because we have that this graph has no cut vertices. So each 3 face will have 3 vertices, and we have that in our assumption we have that the triangle has all the vertices on triangles are 6 plus vertices. So if our rule 2 is that every 6 plus vertex is giving plus 1/3 charge to each of its incident face, then we see that after R2, the negative charge that was there on each triangle is also turning to 0. Why? Because initial charge on each triangle was -1. Triangle has all vertices of degree greater than equal to 6. Therefore, after R2, charge on triangle will be 0. So we also made this negative charge into positive. But this is not the only thing. We have done some changes here. So now what we have done, the earlier negative charges that were there, we have turned them into non-negative. But it might be a possibility that after our redistribution, the earlier non-negative charges have become negative. So we have to show that is not happening. So now we'll show this. So we have seen. So let's first check the charges on vertices. Degree 3 vertex, no charge. Degree 3 vertex, the charge is 0. Now degree 4 and degree 5 vertex, we see there is no change. Why? Because so in the first step, every 3 vertex is receiving a charge, and in second step or second discharging method also the changes is happening to 6 plus vertex. So degree 4 and degree 5 vertex have no change after R1 and R2. And what about 6 plus vertices? Now 6 plus vertices are distributing charge to each of these faces. So earlier charge on 6 plus vertices was dV minus 4, and now it is distributing plus 1/3 charge to each of its faces. And how many faces we have? dV faces. So the total net charge after R1 and R2, charge on 6 plus vertices will be this. And this is what? This is basically 2 dV minus 12/3. And since degree of vertex is greater than equal to 3, this is also non-negative. And now so we have seen that all the charges after redistribution, charges contributed by each vertex is non-negative. Now let's check on the faces. So first of all, triangle we have already checked. triangle has 0 charge. Now 4 and 5 phase. Here also we see that 4 and 5 phase. So among these two steps, every 3 vertex is receiving a charge from each of its incident phase. Yeah, every 3 vertex is receiving a charge from each of its incident phase. But our second assumption was that all degree 3 vertices are lying on 6 plus phase. So the faces of length 4 and 5 have no vertex of degree 3. So net effect, so their charge will be non-negative because it is already non-negative, and some charge they might be receiving some charge from R2, but this will only make them, since they are non-negative and we are adding some non-negative number, it will be non-negative only. Now for the 6 faces. Now for 6 faces, what we are doing, under R2 we see that every 6 plus vertex is giving 1 by 3 plus 1 by 3 charge to each of its vertex. This is done. Every 3 vertex is receiving a plus 1 by 3 charge from each of its incident phase. So now if we have a 6 plus faces, that is faces which have length more than 6, so the charge which is subtracted is in the verse, basically what I am saying, that so the only charge that is being subtracted from faces are coming from R1, and in R1 we have that they are 6 plus phase is distributing plus 1 by 3 charge to each of its to degree 3 vertex. So we see that charge on 6 phase, it will be greater than equal to the earlier charge which was length of f minus 4 minus, and the worst case scenario is that all these 6 vertices are degree 3. So LF by 3, and this from the previous calculation we see that it is nothing but 2 LF minus 12 by 3, which is also greater than equal to 0. So we see that LHS is non-negative, RHS remains unchanged because we are distributing the charges only. Therefore, we arrive at a contradiction. So therefore, what we have assumed is false. And hence this graph has to have a degree 3 vertex on a 5 plus phase or a 6 plus vertex on triangle. Hence we are done. Now the next question. Before going to the next question, let's quickly recall group actions. So what are group action? So for group action, first we require a group G and a set X on which this group acts. So we say that a group G acts on a set X. If we have a map from G cross X to X, where Gx is going to G dot X, and this map should satisfy these two properties. that identity of x is equal to x, that is identity transformation is making no changes to x. And secondly, g dot h dot x should be same as g h dot x. So what we are doing basic in a group action, what we are doing, each element of group is assigned some permutation of x. Each group is assigned some permutation of x. So g is a map from x to x where it is g dot x belongs to x. So this is a permutation of x, and these type permutations should satisfy two property, that identity permutation should remain. So identity permutation should not make no changes to x, and secondly we should have this compatibility, that first if we multiply the group actions, and then we apply then we do it then we act on x, it should be same as first acting on x via h and then via g. So we see that this is what a group action, and giving an action of group g on x is same as giving a group morphism from g to group of permutation of x. So this is what we were doing, that every element of g, so we are assigning to each element of g a permutation of x. So we have a map from g to sx. Now once we have these, then we have few notions. First we have a notion of orbit of x. So orbit of x is all the possible movements of x under g. So we have a set x and g is acting on it. So all the we have a set x and g is acting on it, by which means that each g is transforming x. So orbit of x is basically all the possible positions to which x can move via g. Then the next thing is stabilizer of x. Stabilizer of x is, now the stabilizer of x lies in g. So it is counting all the elements of g which are fixing x, and fixed elements of g is basically all the elements of x which are fixed by g. So this is elements of g fixing little x, and this is elements of x fixed by small g. So now for example, our set A is set of squares on 2x2 board, that is these are the 4 squares, and group G is comprising of two permutations. First is the identity permutation. So how I is acting on A, I dot A is equal to A for all A. And secondly, sigma is the reflection via this diagonal. So how is sigma acting on our set A? So we see sigma dot 1 is 4, sigma dot 2 is 2 because 2 is fixed by sigma. Sigma dot 3, sigma is basically a reflection by diagonal. So 1 goes to 4, 4 goes to 1, and 2 and 3 are fixed. So sigma dot 1 is 4, sigma dot 2 is 2, sigma dot 3 is 3, and sigma dot 4 is 2. Sigma dot 4 is 1. Because 1 and 4 are being swapped and 2 and 3 remain fixed. Now we calculate all those notions that we discussed earlier for this group action and for this set. So first let's calculate the orbits. Orbit of 1. So by orbit we means that we have to look at all the possible position where 1 is going under action of G. So under action of G, under identity 1 is going to 1, and under sigma 1 is going to 4 because 1 is being reflected. So we see orbit of 1 is 1 and 4. And this is also the orbit of 4, you can check. Now orbit of 2, now if we want to find orbit of 2, so what is the image of 2 under identity permutation? It is just identity. And what is the image of 2 under this reflection? It is being fixed, so it is also 2. So we see that orbit of 2 has just one element, which is 2. And similarly we can see orbit of 3 will come out to be 3 and orbit of 4 will come out to be 1. Now next notion that was of fixed set. So fix of 1, that means we want to look at all the elements of G which are fixing 1, which are leaving 1 unchanged. So identity permutation is leaving 1 unchanged, but sigma is not a okay. Fix 1 is okay, sorry. So fix 1 is basically, fix 1 is basically, this is identity. Fixed identity is basically all the elements of X which are fixed by identity. So now identity is not at all changing our X. So we can see all the elements 1, 2, 3, 4 are fixed by identity. And second, we have to find the fix of sigma. Sigma is reflection via this diagonal. So we have to find all those elements of A which are unchanged by the action of sigma. So we see that 2 and 3 remain unchanged. Therefore fixed sigma is 2 and 3. 1 and 4 are not in fixed sigma because under sigma 1 goes to 4, 4 goes to 1. Therefore fixed sigma is just 2 and 3. Sigma. And now the next thing is stabilizer. So stabilizer of 1 in this was what I was saying previously. Stabilizer is in subset of G. So if we have to find a stabilizer of 1, which we are basically looking at all the elements of G which are leaving 1 unchanged. So So what among I and sigma, what is leaving 1 unchanged? I, identity. Therefore stabilizer of 1 is identity. And now stabilizer of 2. So what all elements of G are leaving 2 unchanged? Both of them. So we see that stabilizer of 2 will come out to be the whole group G, and similarly stabilizer of 3 will be whole group G, and stabilizer of 4 is identity. So now once we know what is orbit, what is stabilizer, what is fixed set, and what is the group action, let's go to the next question. Okay. So our next question is this. So we have a group G which is Sn, that is group of set of all permutations on set 1 to n. And here the case is that the set on which G is acting is also Sn. So here both the set and both the group are Sn itself, and the action is the conjugation action, which is just this, that tau dot sigma is tau sigma tau inverse. So this is our group action. So for a simple example, if we are considering S3 is, we see that S3 has identity, then it has these 2 cycles, and then this is 1, 2 rotations. So under this 1, 2, 2, 3, where it is going, this is basically going to 1, 2, 2, 3, 1, 2 inverse, which is 1, 2, 2, 3, 1, 2. So this is the group action. Now some facts about Sn. So Sn is the group of permutation on set of n elements. So in Sn, every permutation can be expressed as a product of disjoint cycles. So this I am stating as a fact, but you can see that on one of the previous lecture when we were doing functional diagram, sir actually proved this. So now we are using now if every permutation can be expressed as product of disjoint cycles, so so we can assign a cycle type to each permutation, and this we can do as follow. So first, given a permutation sigma in Sn, we express it as a product of disjoint cycles. Say we can express sigma as a product of disjoint cycles of length k1, k2 till kk. So since it is a product of disjoint cycles, sum of all these cycles should be n. And suppose these numbers we have listed it down in the decreasing order. So then the sigma will have following cycle type: k1, k2, kk. For example, so now this is the definition. Now for example, in S5, if we have this element 1, 2, 3, 4. So first we see that we have written it as a disjoint cycles. Then the cycle type of this permutation will be 2, 2, 1. Because we have a cycle of length 2, we have a cycle of length 2. This is S5. So generally when we have these one cycle, we don't write it. So 1, 2, 3, 4. Here this is same as when we are writing by convention, we might leave out writing out the one cycles. That is, so if some number is not appearing, that is, it is understood that it is a one cycle, that it is fixed by permutation. And hence we see that 1, 2, 3, since 1, 2, 3 is equal to, when we express it that product of disjoint cycles, since it is like this, so it will have cycle type 3, 1, 1. Now be careful. If the third example is say 1, 2, 2, 3. So this is not this won't have cycle type. You can't convert it into a cycle type because it is not disjoint. So first you make it disjoint. So first, once we make it disjoint, how do we make it disjoint? We start from here. So 2 goes to 3. 2 goes to 3. But 3 is going nowhere here. So we see here 2 also goes to 3. Now 3 goes to 2. In here 2 goes to 1. So this is basically 2, 3, 1. And 1 goes to 2. So we see that this is 2, 3, 1. So this will have cycle type 3, 1, 1. So be careful when a permutation is not expressed as a product of disjoint cycle. First you convert it into a product of disjoint cycle and then write the cycle type. So now once we know what is the cycle type, now the question is, under conjugation action of Sn on Sn, which is the action that we discussed previously, sigma dot tau is tau sigma tau inverse. So our first question is that we have to show that orbit of k cycle consists of all k cycles in Sn. Okay, so let's do this. So A part. So first let's we start with k cycle. So what is a k cycle? K cycle is the permutation of this type, AK, and we have that AK, other elements are fixed. So it is a permutation of this type. And if we want to express, so this is this sigma. So if we want to express it as a function, it is basically that sigma A1 is equal to A2, sigma A2 is equal to A3, sigma AK minus 1 is equal to AK, sigma AK. Now this is a cycle. So AK goes to A1. Sigma AK is equal to A1 and all others. Sigma AI is equal to AI for I greater than equal to K. So this is the permutation. Now we have to show that orbit of this consists of all cycles, K cycles in Sn. So for proving this, first we prove this lemma that if sigma is this, then tau A1 AK, tau inverse is nothing but tau A1, tau A2, tau AK. So we see that So if we have to, so this is, first we prove this, and then we'll see how from this lemma we can conclude that orbit of sigma, that is orbit of k cycle, comprises of all the k cycles. So now we have to prove this. So if we have to prove this, so it is sufficient to find the value. So if this is, say, f, it is sufficient to find the values of f on all the sets. So now, since tau is a permutation, we know that this set A1 till AN is equal to tau A1, tau AN. So if we want to find the function f, either we evaluate on this set or this set, it is same. So let's do this. So what is f of tau A1? F of tau A1 is tau A1 AK, tau inverse of tau A1. So tau inverse of tau A1 is just A1. Now A1 here, A1 goes to A2, and this is, then we are applying tau again. So this is tau A2. And similarly, if you compute, you can see that f of tau AK minus 1 will be tau A1 AK, tau inverse tau AK, which is AK minus 1. So with tau inverse, this tau AK minus 1, this is tau inverse of tau is tau inverse composed with tau is identity. So this give AK minus 1. Now AK minus 1 under this permutation goes to AK. Then we apply tau again. So this is tau AK. And similarly, f of tau AK will turn out to be tau A1. And now f of tau AK plus I. So if we want to find this, now this is identity. This permutation fixes AK plus I. So say here it is this. So we see that this permutation f is also fixing this. So what is our f? F sends tau A1 to tau A2. Tau A2 goes to tau A3. Tau AK minus 1 goes to tau AK. Tau AK again goes to tau A1. So it is a cycle. And rest all cycles are fixed. Rest all elements are fixed. So we get our lemma that tau A1, tau under conjugation action, K cycle goes to K cycle of this form. Now proof of A. Now proof of A. So we have to find orbit of this K cycle A1 AK. Now we have to find the orbit of this cycle A1 till AK. So what is the orbit? Orbit we have, so orbit set is by definition. Orbit set is by definition tau dot, this is under the group action, tau dot, so basically tau and this all possible images. And from our lemma we see that so A1 to so any element in the, so from our lemma we see that orbit O of this cycle is contained in the sigma, where is contained in the set of k cycles, is contained in the k cycles permutation, because when we act on this k cycle by tau, we basically get tau sigma tau inverse was coming out to be a k cycle. So we see that any image in the orbit is here. Any element of orbit is a k cycle. Now we have to show the other way containment. So suppose sigma is a k cycle, say b1 bk. We need to find tau such that tau sigma tau inverse is equal to b1 bk. And from the previous lemma only we know how can we construct our tau. So define tau as follows. So tau ai, define it to be bi if I is less than equal to k. Yeah, tau ai as less than equal to k, and since it has b1 till bk elements, so set of the earlier elements, that was a1 an minus b1 bk, is say, so what I am saying that if this is a k cycle, now we'll have, so this k cycle, this is a k cycle and it is fixing n minus k elements. Let's list down them also like this. So then we define tau as follows, because this is basically any of this cycle is this, and rest of the elements are fixed. So this tau need not be unique. So we define taus as follows. And if we do that, we see that tau sigma tau inverse is equal to b1 bk. There, sigma prime, sorry, this was sigma prime, sorry, I'm doing lots of mistake today. We want to start with some new cycles, sigma prime. So I have already used sigma for the original one, so I can't use this. So this is sigma prime. So we see therefore sigma prime belongs to orbit of a1 ak, and hence we see that orbit of a1 ak will be nothing but sigma, such that sigma is a k cycle. Now I have done this. Now the second part is, so we have shown that orbit of a k cycle consists of all k cycles in Sn. Now second part is that we have to show that two permutations in Sn are in same orbit if and only if they have same cycle time. So this I leave it to you. So prove this using A and fact that I mentioned, that every permutation can be expressed as a product of disjoint cycle. Using this and A, this will be straightforward, so do it. And then third thing is conclude number of orbits equals Pn. So from B we see sigma, sigma dash are in same orbit if and only if they have same cycle type, therefore number of orbits equals to number of cycle types. That is, we have to count the set K1 Kk such that this is a increasing sequence. We have to count this set Kk, and we have additional condition that they should sum up to be n. So what is this? Number of partitions of n. So we are done. Okay, so that was all for today. Thank you.